Okay, the next reaction we're going to look at using enols and enolates is called the aldol reaction. It's one of my favorite reactions. And it involves usually an aldehyde, occasionally a ketone, but almost always it's an aldehyde. So let's make a note, usually an aldehyde. And what you do is you treat this with sodium hydroxide and water. So it is under equilibrium conditions. But the cool thing with this is you can actually couple two of these aldehydes together and make a compound that looks like this. So we've got the alpha position here next to the aldehyde, and then we've got a beta position over here. And so the name of this would be a beta hydroxy aldehyde. And it's a really clever way of making a new carbon-carbon double bond that's pretty gentle. It's a lot less aggressive than using something like a Grignard reaction. All right, so let's take a look at the mechanism. And the mechanism is fairly intuitive, although it's a little bit steppy. And as you can imagine, the first step involves forming an enol or an enolate. So if we have this aldehyde, the only position that has alpha protons would be right here. So this alpha position has protons, and it's got 3 of them. So I'm going to show these alpha protons. And what we're going to do is we're going to have this react with the hydroxide, and we're going to make a really small amount of our enolate. And this enolate, like I said, is going to be a really good nucleophile. But we're not going to be making very much of it, right? If we think about this equilibrium, very little of it will actually be the enolate. The rest of it will just be floating around in equilibrium as starting material. But the neat thing with this is that your unreacted starting material can act as an electrophile. So this confuses students, but this is basically unenolized starting material. It's still in solution. So the enolized starting material can react with any of the unenolized starting material, and as a nucleophile, it can attack into the aldehyde as an electrophile. Now, if you remember, aldehydes are a lot more electrophilic than ketones, which is why up here I made that note that usually these reactions involve an aldehyde, because we need to have a relatively electrophilic substrate. All right, so in this next step, we're going to get a new carbon-carbon bond to form. And this carbon-carbon bond, when we think about it, is, right here. So we've kind of linked that together, and then we've got our new intermediate. All right, but we're not quite done yet. We still need to protonate our product, and if you remember, over here, we used hydroxide, so really we do have water floating around now. And so if we have water floating around, that can act as a weak acid source and protonate our product to give us our neutral organic intermediate. The neat thing with this is that the base is regenerated, which means that it is catalytic. We put it in the beginning and we get it out in the very end. So it's a neat reaction. It requires really somewhat gentle conditions to form a new carbon-carbon bond. The interesting thing is that this is all reversible. So the reverse reaction, I did want to cover really quick. It's called the retro-aldol. Retro, in terms of organic chemistry, just means going backwards. And with the retro-aldol, everything's basically done in reverse. So let's imagine that we have that same product that we just made, and we have that hydroxide that we just made. Well, this hydroxide could grab that proton and make a negative charge on that oxygen. and we could have water as our conjugate acid. And then in the next step, we could basically kick this off as a leaving group. Normally we don't ever see carbons being kicked off as a leaving group, but in this case, that carbon getting kicked off as a leaving group, meaning this carbon right here, is somewhat allowable because this leaving group is resonance stabilized. All right, so when we do this, we're going to be working backwards, and we still have our water floating around. So the water could donate this proton back, and we could be left with our aldehyde plus our hydroxide. So these reactions are very much reversible. The position of the equilibrium depends a lot on the stability of the beta hydroxyaldehyde versus the stability of the starting materials. It prefers to be on the side of the equilibrium that is more stable. All right, so it is really important to note that this reaction works best with aldehydes. And the reaction is reversible. Just like I showed you here, you can get a retro-aldol reaction to take place. So then the question is, well, why would you want it to be reversible? Well, we can drive it out of equilibrium. We'll talk more about that in a second. But let's do a practice problem first, just to kind of review. And this one, I think, is good practice. And what I like to do is color code everything. You're welcome to do this in your notes as well, but it helps me avoid any confusion. So let's say on an exam, I give you this compound. We've got an aldehyde, and we're going to treat this with sodium hydroxide, and we're going to treat this with water. And on an exam, I might give you a box and say, all right, show me what the product would be for this. Well, let's do the mechanism. Well, we know that if we have the starting material, that there's only one alpha position with protons, and that's right here. And we've got two of these protons. So if I were to treat this with hydroxide, well, we could grab one of these alpha protons and we could make a small amount of our enolate. Where we have a negative charge on that carbon. All right, but like I said, not all of our starting material is going to form our enolate. So what I'm going to do is I'm going to show a green molecule over here, and this is just going to be color-coded as my unenolized starting material. I'm just using a different color so we can keep track of everything. All right, so in the next step, we're going to attack into this unenolized starting material. And we're going to form a new carbon-carbon bond, and I'm going to show that in orange. And we're going to attack into that green reagent. So I'm going to have an oxygen with a negative charge, I'm going to have a hydrogen, and then I'm going to have a phenyl group over here. So that's the green equivalent that we've added into. All right, and then we still have water floating around. Water is going to be our weak acid. So we can protonate this intermediate, and we can get to our final product. So this does look big and scary, but what I found with students is that it's a lot less overwhelming if you color code everything and if you just draw out the mechanism. I know on exams it can be a little daunting where you think this should just immediately pop into my head, but there's no shame with drawing out a full mechanism and color coding everything. In fact, I oftentimes do that too, just because it helps me out. All right, So let's take a look at an offshoot reaction. So we already did this practice. This next reaction is called an aldol condensation. And it's important to remember that condensation stands for something. It means that you usually kick off water. Or another small molecule. Usually it's water though, but once in a while you'll see condensation reactions that kick off other small molecules. So this is a similar reaction, but as you can tell by the name, we've got to lose oxygen. Specifically, we've got to lose water. So I'll show you how this works as an overall reaction first. And it's the same idea as before. So if we have an aldehyde, and we treat this with NaOH and water, at equilibrium, we can do the aldol reaction that we were just previously investigating, right? So this would be our beta hydroxy aldehyde. And this reaction right here is just called the aldol reaction. However, we can push this even further by adding heat. And so I'm going to use that delta symbol for heat. And when this happens, we can push this reaction even further, and we can make an alpha beta unsaturated aldehyde. And this whole reaction is called an aldol condensation. As you can tell, we've lost this OH group, that beta hydroxy position, and it's going to be kicked off as water. The other important feature of this reaction is when we apply heat, we're no longer under equilibrium conditions anymore. And the reason for that is by getting this alpha beta unsaturation point, meaning that double bond, we've extended conjugation. So now we're going from double to single to double, and by extending that conjugation, we're making this a lot more stable, and it's no longer going to be a very reversible reaction. Okay, so let's quickly take a look at the mechanism for the aldol condensation. And I'm not going to go through the entire process because we've already covered at least the first half. And that's the part where you take your aldehyde and you react it with your sodium hydroxide and water, and you're able to make your beta hydroxy aldehyde. So we've already seen this mechanism, but what I want to do next is really focus in on the next part. And like I said, this hydroxide is catalytic. And when we think about our product that we just made, this beta hydroxy aldehyde, we still have some alpha protons coming off of the remaining, or off of that alpha site, right? So what we can do next is we can have this grab one of these alpha protons and make a conjugate base. And the neat thing with this conjugate base is that it has resonance stabilization, right? So this negative charge that we've made can be delocalized up to that carbonyl oxygen. But either way, this is a valid resonance form. Let's go ahead and draw both, just for fun. And we can show this using either resonance form. All right, so we've got this conjugate base that's resonance stabilized. The next step is pretty interesting. What happens is this negative charge comes down, kind of cascades over, and kicks off hydroxide as a leaving group. And this occurs under high temperature conditions. So when we do this, we're able to make a new double bond specifically a double bond between the alpha and beta carbons. We kick off hydroxide, meaning it's still catalytic, and we generate water. So we've got all three of these things coming off in the end. So the question is, well, why might this be favored? Well, there's a few reasons. Normally hydroxide's not a good leaving group, but let's think about the heat. So if we think about this reaction, we're increasing disorder, meaning we're creating more moles of our product. So increasing disorder favored at high temp. That's one reason why this reaction will proceed forward, even though hydroxide's a terrible leaving group, is we're just pushing it with heat, we're taking advantage of entropy. The other reason is kind of interesting too, and that has more to do with conjugation. So if we look at this, we've got a double bond, we've got a single bond, and we've got a double bond. By extending conjugation, we're making a more stable product. So extended conjugation. And because of this, we're no longer dealing with equilibrium conditions, but rather a one-way reaction, meaning once we form this, we're kind of stuck there. We're really not going to go in the reverse reaction to any appreciable extent. All right, so let's take a look at a brief summary here. If we have an aldehyde, we can really quickly form this beta hydroxy aldehyde. Typically, when you do this under normal conditions, you get about 70-ish% of the beta hydroxy aldehyde, but it's still under equilibrium, right? 20% is still going to go, or is still going to be your starting aldehyde. However, if you run this at high temperature, you can favor this condensation product. And we said that that has to do with increasing disorder, meaning we're kicking off water, and we're extending the conjugation of the system. If you have a highly conjugated system, sometimes you don't even need very high temps in order for this to occur. In fact, in our solventless aldol lab, you'll see in the video, I don't apply any heat. This occurs at room temperature because the system desperately wants to extend conjugation out. All right, so that's where we're going to stop. When we come back, we're going to take a look at a lot more examples with these aldol reactions.